everybody. Thank you for making time out of your day to come to this presentation. Over the past 9 weeks, I've been working on this project focusing on the EX400, evaluation of a novel nanoparticle profiling device for early disease detection. A little bit of background. Exosomes are produced by all living cells in every single living organism. They're a sort of collection of biomaterial found inside and outside of the cell, and they can tell us a lot of information about the cell itself. They're important for several processes inside of the body. They can regulate things like cell intercommunication, disease response, and they've recently come into focus for their potential for early cancer diagnosis. Cancer cells also produce exosomes, so if we can find a way to detect these cancerous exosomes early, we might be able to develop a new method to diagnose cancers sooner. The difficult thing is exosomes are very, very small. They're several times smaller than cells themselves. We've developed a couple of technologies to image exosomes and detect them. These can be used with all nanoparticles in general. Some common ones are particle tracking analysis and a variant of it, nanoparticle tracking analysis, as well as static or dynamic light scattering. The basic principle of both of these is that a laser is shown through a solution of particle, the angle is strange, a particle solution. This laser bounces off of particles within the solution and into some sort of detecting device, excuse me. For particle tracking analysis, a laser is shown into this particle solution, which is on top of a metallized surface right there, reflected into a microscope. For static and dynamic light scattering, this laser light is shown directly through the medium and into a camera. Both of these very accurate, but they have a limited ease of use when working with biological samples. Excuse me. So particle tracking analysis requires you to have a multiple use plate. You put the sample into the same reservoir over and over again, which can be difficult if you're working with biological materials. Static and dynamic light scattering are very accurate, but they require you to use a homogeneous solution, or a solution that only has one kind of particle inside of it. That is very difficult to create with a biological sample. It requires maybe days and days of filtering and processing, and it makes research slower. So there's an apparent need for a better way to image nanoparticles that are of biological origin. The University of Tokyo, in collaboration with the Innovation Center of Nanomedicine, has created the EX series of machines. The EX400 images particles using dark field microscopy. Videos are taken of these nanoparticles as seen here, and their movement is processed by software, and we can use those videos to calculate their hydrodynamic diameter. The equation for calculating that diameter is right here. I have over here the Boltzmann constant, multiplied by temperature, divided by 3 pi. That right there, which looks like an N, that is the Greek symbol eta, which is the solvent's viscosity, and this is dt, which is the diffusivity constant. A little bit about hydrodynamic diameter. If you're not familiar with it, the hydrodynamic diameter is the same size sphere that would diffuse at the same rate as whatever it is you're sampling. This is used very often in biological settings. Things like proteins and enzymes are not spherical very often, so it's very useful to find a way to approximate their size with a spherical model. When you're working with spherical samples themselves, the particle's actual size will be a bit smaller than its hydrodynamic diameter. So, what are the objectives for this project? Evaluate the precision and accuracy of the EX400 across a whole range of different nanoparticle diameters, and demonstrate its performance against similar devices. How do we do this? So we selected 2 devices to represent 2 different nanoparticle sizing methods, The Zetasizer Nano ZS uses static and dynamic light scattering. That's primarily used for proteins. The NanoSite LM10 is used with particle tracking analysis. Both of these, again, are very commonly used in biomedical settings. We prepared samples of particle size standards from NIST. These are really easy to prepare, and we know for sure what size they are every single time. Another bonus is that these are designed to not clump together when you're measuring them, which is really useful when you're working with nanoparticles. We measured 8 total different diameters, listed right there at the bottom. These are what we put each sample into. Over here is a disposable cuvee, which was used with the Zetasizer. Over here is a NanoZS metallic platform. Over here is a microfluidic chip that was used with the EX400. 3 trials per sample, 3 trials, 4 trials. This discrepancy right here, 3 trials over here, 4 trials over here, is just how the machines worked. The Malvern Analytical and the NanoZS proprietary software just ran using 3 trials. So what did we find? After measuring each sample of different diameters, this is the data we got. If you look over near the bottom, that yellow graph right there is the EX400. That blue graph right there is the Nanosite LM10. We can see at the lower end it starts struggling a little bit to give an accurate measurement. That suggests a lower limit. There might be particles that are just too small for us to measure using these devices. Zetasizer NanoZS was accurate using both operating wavelengths throughout. If we look and we focus on just the results from the EX400 and the actual size of each particle, we can see that this line is almost parallel. And if we throw away that bottom bit where we don't have any good data and we create a linear regression, we see something really interesting. This line of best fit is parallel to the actual size of these particles. Further, the R-squared value, which is sort of how well this line fits our data, is very close to 1. What does this mean? This means that for every input you give to the EX400, you're going to get a reliable output every single time. So some discussion. Why is the EX400 overestimating this particle size every single time? Why is the line parallel? So if we go back to talking about hydrodynamic diameter for a little bit, we have 2 different particles of different sizes. One is smaller, one is larger. And you can see here there's this difference between its actual size and its hydrodynamic diameter. We'll just call that the buffer for short. If you look at different particles of different sizes, you'll see that they actually have the same size sort of buffer, the same difference between their actual size and their hydrodynamic diameter. So buffer size remains constant between if it's the same material through different diameters. So a constant overestimation of about the same size tells us the EX400 might actually be accurately measuring hydrodynamic diameter. So a quick summary and conclusion. Current technologies are very accurate, but they can be difficult to work with in a biomaterial context. There's a need for new devices to be developed to make it easier to work with biomaterials. We developed the EX400 and we found it to be accurate at measuring hydrodynamic diameter at different diameters. Thank you very much. Some acknowledgements. Thank you to the people from the University of Tokyo for helping me along with this project throughout the summer. Hiroko Ito from the Innovation Center of Nanomedicine for introducing me to the company, helping me before I came to Japan. Thank you to Angelica Fassi for helping me with this presentation. Thank you to Timothy Myers for sponsoring my research in Japan. Any questions from the crowd?
So, audience, if you have a question or comments, please raise hand on the body. Especially students. Hi.
Thank you for your presentation. It's very interesting. If precise measurement is achieved, how can we become to do?
Sorry, could you repeat the question?
If precise measurement for exon is achieved, how?
Oh, what's the benefit of measuring?
Yes.
Oh, yeah. So accurately measuring exosomes can tell us a lot about where they come from. So if we know a cancerous exosome is, let's say, 30 nanometers large, if we find a bodily fluid that has exosomes 30 nanometers large from this specific part of the body, that can give us an, hey, maybe these are cancerous exosomes. The EX400 can also measure a particle's electrophoretic motion, which is a very large word, which is another useful parameter when trying to figure out more properties about that particle. So in short, getting accurate readings on exosomes can tell us more about where they come from.
Thank you.
Students. Thank you for your presentation. Can you show me the result, please?
So I think the graphs.
Yes.
Okay. It is.
Yes. And please go to the next page.
Yes.
Yeah.
You showed no, two particles.
Two part. Oh. Here we go.
Yes.
Okay.
I want to know that when you change the solution,
Mhm.
the the difference
Mm.
between actual size and hydrodynamic diameter will change.
No, so actually what I was trying to illustrate here was that they stay roughly the same, even if these are two differently sized particles. The difference between their actual size and their hydrodynamic diameter will remain roughly the same. Does that make sense?
Okay, so you mean when the particle size is different,
Mm-hmm.
but the buffer size will be equal.
Yeah, yes.
And I think that is because of the solution.
Mm.
So if you change the solution,
Mhm.
the
Oh, I think I understand. Instead of water, using a different. Oh, yeah. That's a really good question, actually. I do think that the buffer size would change. Hydrodynamic diameter is partially dependent on what medium you're dissolving your particles into. So if we look back at the equation used to calculate hydrodynamic diameter, we can see that one of the variables is the solvent's viscosity. So to answer your question, yes, because the solvent's viscosity would change, the hydrodynamic diameter and therefore the buffer would change. Is a good question. Did that answer your question?
yes. So do you think when you change the solution,
Mhm.
but the difference
Mhm.
will be same?
I think it would be different. I think that buffer size would change depending on what medium you use to dissolve, or what dissolving medium you use. Excuse me. Thank you.
So, any other comments?
Before students.
Okay, so please think your question. So I have.
Yes.
So you tried our EX400 machine
Mm.
as a beginner, right?
Mm.
We want to know beginner's advice. So when you use EX400, if you find some difficulty of using or difficulty of software, or if you have some advice from your side, please give us.
Yeah. So the EX400, it's a very fancy machine, honestly. It can be difficult to understand how to use it at first. I think it comes with the nature of developing new machines. At first, you're focusing more on having the machine actually work instead of designing maybe a friendly interface. I think it was a little difficult at first to understand how to use the machine. Thankfully, I had a very good mentor in Mizui-san that taught me how to use the machine. I think once I was shown how to use the machine a few times, I understood it and I was able to work with it quickly. I can give you an email talking more in depth about some things with the EX400 I found difficult with.
Let's discuss it.
Yes. Thank you.
そう、いけそうこれはいい練習になるかなと思うんですけど、せっかくだから話してみてほしいな。
Yes.
So can you show me the graph?
Yes.
So I wonder the yellow graph walked rapidly at the very left side.
Yes.
Yeah. So
Got you.
I want to know why that thing is happening.
Yeah, that's a very good question. So, just to confirm, your question is why is there this big jump at the bottom?
Yeah.
Okay, here. So, inaccuracy at lower sizes. It is very difficult to find these very small nanoparticles. 20 nanometers is obscenely small. We think that there was a large spike in estimated diameter because the EX400 was measuring image artifacts. We had to turn the brightness extremely high to be able to even begin seeing these particles, which created a lot of sort of illusions near the tops and bottoms. We think the EX400 was measuring these artifacts and including them in the data set, which is what caused that big jump near the bottom end. Does that make sense?
Probably our system can eliminate such peripheral collisions from the analytical regions. Is that right?
Yes. But,
Of course. 外すんじゃないの?
yes. So,
So we can determine the size of ROI, ROI by ourselves.
Yes.
So how we can eliminate the unnecessary areas.
Yes. Definitely, I would need to go back. If we limited the ROI to maybe around here, it might give us less image artifacts. That's a very good point, and I can look into that more.
Also, so actually you measured 20 and 50 and 80 meters.
So we measured.
20, 30.
Yes.
So what is the lowest particle size you can measure using nanosite? They usually say the detection limit is 50 nanometer or something. But in your data, you tried for 20 and 30 nanometers.
Yes.
So can you show the graph?
Yes.
So there's some problem for 20 and 30 nanometer.
Yes. So I believe.
And it is also the same for our system. So actually, the synthesizer provides the similar values for standard particle diameter.
Yes.
And actually, the NTH system, that means EX400 and nanosite always shows that something somehow higher values.
Yes.
Nanositeもそれをまあうちのもついてる。
はい。
how about the buffer solution? So, what kind of aqueous solution you suspend now standard particles?
In water,
In water.
in millicube.
So everything is the same.
Yes.
The same.
Everything is the same.
So you try to explain the difference between the true diameter and high diameters by by the difference between the
Yes.
actual and high diameters.
Yes.
But this hydro diameter is usually the difference in the place where do you know the potential? The potential じゃないな。This hydro diameter is sometimes called slip plane. Slip plane is
Yes.
so on solid surface, some aqueous, water molecules are strongly attached. So it makes the apparent increase in that size diameter. Such a such layer is sometimes called Stern layer. Stern is the name of the physicist, and so he explained on the at the interface between solid surface and water. There's some very sticky water molecules on the surface, and it is called Stern layer. And usually the Stern thickness of the Stern layer is less than 1 nanometer or something. So in this case, the difference is about several tens nanometer. So the explanation is not hard.
Yes. Thank you.
So please check. So I will give you some keywords. So please check this word. So Stern layer and slip plane.
Okay.
Okay.
Okay, so it's almost time. So if any other comment or question, if no, okay. So thank you, Julian. So we want to go party. Okay.
Okay, thank you very much.
Okay. So let's applause to him again.